This video is an overview of the Flame Extinguishment Experiment, or FLEX, that we are performing at Glenn Research Center during this increment. FLEX is performed using the MDCA chamber insert assembly, which you see here being removed from the Combustion Integrated Rack, or CIR. MDCA, or the Multi-User Droplet Combustion Apparatus, is designed to support multiple droplet combustion experiments that investigate fire safety and the science of burning liquid fuels. The chamber insert assembly houses the fuel reservoirs, needles, igniters, and fiber that are used to perform a test point. It also houses the MDCA color camera, which provides real-time video of hardware setup and the combustion event. To learn more about the fundamentals of flames and fire suppression, FLEX searches for the flammability boundary in different ambient environments. The flammability boundary defines the environment where a steady flame can exist, or the flammable region, and the environment where a steady flame cannot exist. Fuel droplets that start inside the boundary will burn steadily, get smaller, and eventually reach the red side, where they either diffusively extinguish or burn to completion and disappear. Diffusive extinction occurs because, as the droplet gets smaller, the fuel and oxygen don't have enough time to react, causing the flame to extinguish. Fuel droplets that start outside the blue boundary will ignite but not burn steadily. The flame will get larger, and then the burning droplet will radiatively extinguish. Radiative extinction occurs because, as the flame gets larger, it loses energy faster than energy is being generated by the burning droplet. The flame grows until it cannot sustain itself and extinguishes. The diffusive and radiative limits meet at the limiting oxygen index, which is the minimum oxygen concentration that can support a steady flame. For FLEX test points, we vary the initial fuel droplet diameters and the concentrations of oxygen, nitrogen, and the diluting gas in the ambient environment to find the diffusive and radiative limits. We also perform diluent exchange tests to isolate the effect of the diluent, or diluting gas, on the burning droplet. These tests use the same oxygen concentration while varying the pressure and the concentrations of diluent and nitrogen. This increment we're investigating xenon and helium as diluents, which will provide useful comparisons to earlier tests with carbon dioxide. This video of a FLEX test point shows methanol fuel being dispensed from one of the needles. This test point is based on a pre-EVA ambient environment that's been diluted with helium. In high-speed video, the droplet gets bigger as fuel is dispensed. When the droplet is the correct diameter, the needles are stretched to its edges, which causes less force to be imparted during droplet deployment. The MDCA color camera zooms out for a larger field of view. Once the camera light goes out, the needles will simultaneously snap away from the droplet, leaving it free floating. The hot wire igniters ignite the droplet. This test is well within the flammability boundary, which means that if a fire were to break out when operating in this pre-EVA ambient environment, diluting the environment with this amount of helium would not be enough to suppress the fire. The droplet burns with a bright visible flame, then transitions to diffusive extinction. This video shows a test point that uses heptane fuel in a standard air environment that's been diluted with xenon. This test will have a relatively short burn time followed by radiative extinction. After extinction of the visible flame, you will see what is possibly the cool flame phenomenon, which we discovered during previous FLEX test points. Ignition of the droplet starts the conventional hot flame stage of combustion. After radiative extinction of the flame, a period of low temperature combustion occurs that causes the fuel droplet to continue rapidly evaporating without any visible flame. This observation suggests a possible cool flame stage. Prior to the FLEX discovery of cool flames, few, if any, experts believed they could occur as a steady flame around a droplet. Cool flames typically occur in premixed systems, are not steady, and lead to a hot flame ignition. Evidence of cool flames have been observed in liquid fuel combustion engines, where they cause engine knock and limit engine efficiency. Even though you can't see a flame, the cool flame stage of combustion still poses a unique fire hazard because after extinction, it leaves behind a large vapor cloud that can remain suspended almost indefinitely. If an ignition event or fire were present, this cloud could potentially burn or enhance burning. The next video shows that, under the right conditions, it is possible for the cool flame stage to transition back to the hot flame stage. On this heptane fuel droplet tethered to the fiber, you see the flame transition to radiative extinction, followed by the cool flame stage. After several seconds in this stage, a brief flame flash signals the spontaneous reignition of residual fuel vapor, followed by yet another cool flame stage. And then a second flame flash interrupts the cool flame stage again. Results from FLEX will lead to a better understanding of the fundamentals of flames and how best to suppress fire in space, as well as ideas for more efficient utilization of liquid fuels on Earth. Discovery and investigation of the cool flame phenomenon could also lead to more environmentally friendly fuels that get better gas mileage and create less pollution, and improvements in fire safety for space vehicles, such as new safety procedures to deal with invisible fire hazards. We hope this video helps to explain the science of CIR MDCA FLEX. We truly appreciate all your hard work that keeps us doing science on station. We couldn't do it without you.